Okay, so let's continue. So here we are going to implement this inference of multivariate Gaussian distributions from scratch. So here, say we have this d equal to 2. This is my mean. Mean is 0 and 1. And this is my covariance matrix. We know this is a positive definite matrices. So the first thing is we need to sample the x from the normal distributions, right? So, and here the way that we do it is we are going to take something called Cholesky decompositions, such that this covariance actually becomes L times L transpose, right? So this is basically a decompositions of this covariance matrix into L times L transpose. Then what we do is we sample this and Gaussian distributions with the form that is y equal to L times x plus mu. So and x actually follows standard Gaussian distributions, basically 0 and 1s. So if x follows 0 and 1, so which is got and standard and Gaussian distributions, then the y will follows. Then the y will follows the Gaussian distributions with the mean and the covariances. So here it's not just one, that would be identity here, right? Because we are talking about multivariate in the situations. Here we actually sample this at 500 points. So this will be 2 by 500. So each column that would be and for each column that would be 1 samples of y. Okay, so right here we just write out this in PDF for the multivariate normal. So it's just we're using all these packages information to calculate this term explicitly, right? And we can actually plot this contours for this multivariate and multivariate so Gaussian's PDF. So I mean, if we actually plot this out, and you can see this sample data is roughly like an ellipsoid. So you can see this example from this bivariate normal distributions. So obviously it's dense in the middle, it's sparse like outside. All right, so and we can using this sample say we don't know the ground truth of mean and covariances, and what we can do is we can actually use the MLE estimator and to see how good or how bad we are getting here. So in fact, we can using the sample mean, which is 0 and 1 right here. So I mean, this is 0 and 1, and so ground truth. But the sample mean is 0.01 and the 1.014. So this is quite close. So in terms of the accuracy, the relative error is about less than 2%. So this is quite reasonable. On the other hand, you can do this an example covariance here, and you can just simply using the inbuilt function of covariance. You can just directly calculate the covariance of y. But I want to remind you that and the y is 2 by 500. So this is something that you have to be careful. You have to and make sure the dimension of the data is on the is on the row. So this will be d by n and matrix. Then you can directly apply the covariance matrix. So if you directly apply the covariance matrix, you're getting this value right here. So you can see this is quite close to the ground truth. We know the ground truth is 1, 0.8, 0.8, and 1. Okay. Then in terms of relative error, that's less than 1% in terms of 2 norm. So this is quite quite reasonable. So so we actually using this like sample data to estimate the mean and the covariances for this multivariate and for the multivariate Gaussian distributions. All right, so that is the inference, implementation of the inferences. So we talk about how to do the sampling, and also we actually plot this out for the data, and we can use data and to estimate the mean and the covariances with our MLE estimators. Okay, so let's go back to the notes. So so the first thing and this is a like kind of quick review, but in fact this whole idea can be extended. So basically so we can using this idea to actually imposing clustering. For example, right here. So let me just and look at the figures right here. So here we only have a 1 Gaussian. So this is actually just 1 Gaussian. So you can see this is actually the densities. So this is roughly follows the and the distribution of densities. So it's sparse outside of this an ellipse, so it's dense inside of this ellipse. But we can work on like multiple Gaussians. For example, we have like 3 Gaussians, combination of 3 Gaussians, 1 Gaussian, another Gaussian, and third Gaussians. Each of this has its own means. So this is something called mixture of Gaussians. Okay, so this is something that's very important. So, and you can think about this as a clustering problem that we actually have a 3 cluster, 1 cluster here, another cluster here, and another cluster here. So, and each cluster or within the cluster, we assume this is a Gaussian distributions. But in total, we can think about is like ensembles of 3 different Gaussians with a different mean and a different covariances. All right, so so let's just formulate things a little bit. So we can think about this GMM like a Gaussian mixture model is kind of natural extensions of single and the single multivariate Gaussian distributions. So Gaussian mixture models. So the assumption is this my training data. Is actually independently sampled, independently sampled from K clusters from the following like generative process. The first thing is for ith point. So it actually follows like a 2-step process. So first is we're going to generate its cluster membership. We generate its cluster membership. So we need to identify which cluster it comes from. So this actually comes from Z of I in 1 to the K. So say we have a K clusters from some like multinomial distributions. From some multinomial distribution, which is pi 1 to pi K. with probability zi equal to c equal to pi c. Right, so this is actually, we roll a dice and decide. So this I data should coming from the following clusters with distributions of pi 1 to pi and pi k. Then conditional on, like, given we have picked the right and pick the corresponding cluster, so that would be called, and cluster C, we're going to generate an x of I from its corresponding Gaussian distributions of n of mu c and sigma c. So the PDF of this is the following. So it's basically 1 of square root of 2 pi power of d determinant of sigma c and the exponential of minus 1 over 2 x of mu c transpose sigma c inverse of x minus mu c. So, and that's my training data. So my training data is I actually only observe the samples of xi. So my parameter here is nothing but like all the like cluster membership, and so like unknown, like unobserved parameters is cluster membership. I have no idea what is z of I. So this is latent. It's hidden here. And second thing is the model parameter. So this will be pi of c, mu of c, and sigma of c. And this c is from 1 to k. So we need to infer all these and the parameters and also this cluster membership. So this is automatically becomes a clustering problems. So this is actually clustering. And so this is clustering problems. But instead of and the previous we only assume we only have a one Gaussians, but we have a multiple Gaussians. So like basically we ensemble the Gaussians. And actually then we're going to infer the parameters for all these Gaussians and the membership of the so cluster membership for each and the data point. So which it's automatically being considered as a if we can infer this like cluster membership of zi, this is basically what we're doing, the clustering problems. Okay, so the goal is very clear. It's given my training data, 1 to the n, I want to infer the parameter which is pi c, mu c, and sigma c. This c is 1 to the k, and recover the clusters. So basically, I want to find out the z of I from I to the n. Right, so we have inferred the parameter and and work out the clustering problem. Okay, so and this is the whole idea, but we can actually look things a little bit closely. So we can interpret how and what does this assumption means. For example, the ratio of the point right here of the K cluster will be pi1, pi2 to pi K. So if we have a 1,000 data points, say, so we have a 5 cluster, and each cluster that will have 200 points. That means the ratio is just 1 by 1 by 1 by 1 by 1, right? And we have 5 ones. So this is, I mean the actual and the ratios here. And also the points are kind of like distributed roughly over this ellipsoid around this mu1, mu2, and mu3. So this is actually the center of the ellipsoid. And this density of the point is actually determined by the corresponding covariance matrix. So this is basically, I mean, if we know all these and a membership, we can just extract and those points actually samples to the corresponding Gaussian distributions. Then we can just easily find mu1 and sigma 1, right? So, but of course, in general, we don't know which data it belongs to. So this is it's a balance. It's we don't know both of that. Can we find an algorithm to actually trying to and not only find out the membership, but also find the corresponding parameters mu and sigma 1s. So this is and the typical pictures of the mixture of 3 Gaussians in 2D and spaces. And of course, things could be much more complicated, and the data could live in much higher dimensions. But you can see this is kind of much more generalized, because in K-means we assume all these Gaussians, the cluster are more like round shapes. But here, we can allow my datas, or each cluster can be distributed like an ellipsoid. And this actually significantly generalize the K-means clusterings argument. All right, so okay, so let's. Since this is a two-step process, we can actually combine them together to calculate the PDF for the Gaussian mixture models. PDF of for Gaussian mixtures. I want to remind you, this is my parameter, right? So that I want to infer. So probability of X conditional on this parameter. Okay, so this will be, we can modularize all possible and membership Z equal to C. So this is basically summation C from 1 to k, probability X that Z equal to C, conditional on these parameters. All right, so then so we can using the Bayesian's argument. So this becomes the summation C from 1 to k, probability C Z from C, conditional on pi C, C from 1 to k, and the multiplications of so this is nothing but the definition of conditional probability this is mu c sigma c from 1 to dk. Right, because to determine the z equal to c, it only depends on the pi c. To determine the x conditional on z equal to c only depends on the mu c and the sigma c. So basically, these two parameters are completely separated because these are the two like independent and a process. I think I mentioned this right here. And step 1 and step 2. So this is step 1 and step 2. So step 1 and step 2 are independent. So so if we allow this, this is basically summation of c from 1 to dk of pi c of probability x conditional on mu c and sigma c. So this pi c is actually the multinomial distributions. As I said, we can just assign this to be a multinomial distributions. And which is the probability to choose the cluster C. So that means we have the property that summation C from 1 to dk of pi C is equal to 1. Right, so because this is actually the definition of the multinomial distributions. The second part right here will be the PDF of C Gaussian right, and generate the point of x right here. So this is basically a Gaussian distributions with the mean of mu c and the covariances of sigma c. All right, so a little bit like plot right here, you see, and we have 3 different Gaussians with different means and different covariances. If we actually weight it with pi c, and pi c could be just and in this case there will be 0.5, 0.3, and 0.2. The contours of the PDF will look like this. In terms of function, it looks like this. So you can see this and the so like Gaussian mixtures and the distributions can approximate a lot of like irregular and the distributions. So you can see right here is actually the contours of the Gaussian mixtures. And this is basically the surface plot of and of the whole PDF. The goal is if somehow we sample those points right here, we want to click and correctly identify which and the Gaussian cluster it should belong to. So this is the goal. Of course, we can work very similar to those with MLE estimate. So MLE for Gaussian mixture. So and also we know, the likelihood and the whole likelihood, and so we call this as theta, right? So I'm going to call this as theta. So the likelihood of theta is actually multiplications I from 1 to the n of probability x of I conditional on theta. So if we want to maximize the L theta, it's actually equivalent. We don't work out the log and the log and the likelihood. Like directly, I'm actually minimize the negative log likelihood. Okay, so this will be that will be equivalent. But the issue is this MLE problem, unlike the Gaussian models, do not have any analytical solutions. And we're going to show you why. And more importantly, it's not easy to using gradient method as well. One of the reason is one of my parameter here is this covariance matrix sigma here. But we assume our sigma has to be positive definite. It's not only the symmetric, has to be positive definite. So this in general is a very, very hard constraint here. So I mean, if the constraint is quite hard and also and it's very hard to satisfy, it will be difficult to using gradient methods, because if we just using gradient methods, this constraint could easily being violated. As a result, that would that caused a problem in the gradient methods. So we're thinking about trying to minimize this problem without using gradient methods. Right? Why? Because the constraint that the sigma is positive definite is it's very hard to so this constraint is this like specific positive definite like constraint it's very hard, and to make this and the whole optimization problem very, very hard. Okay, so in the next lectures we're going to talk about this in great details, how to optimize these problems and how to optimize that without using any gradient informations, like what we did in the k-means, because in the k-means we also didn't use any gradient informations. All right, okay, that's it for this part.